Welcome back to part 2 of our series Dave Does Math from Home. This is part 2 of our section 3.8 Implicit Differentiation video. Part 2. In the first one we talked about where this comes from. It's Leibniz notation crossed with the chain rule. And we did a quick example. I'm going to see if I can do a more difficult, more weird and abstract example that I think hopefully will match what I put on the board at the start of the first video. I think what I had was sine of y equals 3x squared plus y. This is an implicit function. It is not solved for x or for y. I want its derivative. And its derivative is dy dx. So, we start this process just by taking a derivative of the entire thing, piece by piece. The derivative of sine of y is cosine of y, except now we have to get the chain rule involved. In case y is some function of something, we need to add a dy because of the chain rule. Derivative of 3x squared should give me 6x dx, and the derivative of y should give me dy. Or, if you prefer, 1 dy. So this is the derivative step. And all of these derivatives are things that you know how to do. You've practiced with these a lot. You know that sine becomes cosine. You know the power rule. You know all of this. The only thing that's different now is that because of the chain rule and because of the uncertainties surrounding what is and isn't a function, we're attaching dy's to these things and dx's to these things. After this derivative step, a good way to check your work is every single piece should have exactly one d attached to it. This has a dy attached to it, this has a dx attached to it, this has a dy attached to it. Every piece needs exactly one d. If you have a piece with 2 d's, or if you have a piece with 0 d's, it means you did something wrong. Every piece needs exactly one. Once you've successfully finished this derivative step, the next thing to do is algebraic manipulation until you get a dy over dx. In this case, we have 2 dy's, so we're going to need to consolidate these pieces so that we can factor out the dy. Once you subtract dy from both sides, you have cosine y dy minus 1 dy equals 6x dx. So now all of my dy pieces are on the left, all of my dx pieces are on the right, and I can factor this stuff out. Dy times cosine y minus 1 equals 6x dx. Once you have these things factored out, you can divide everything by dx to get it in the denominator over here, and you can divide everything by 6x to get that. No. That's not correct at all. You don't want the 6x over there. You want to divide by cosine y minus 1 so that this dy dx gets isolated. So, once you do this division, you're left with dy dx equals 6x over cosine y minus 1. And that's it. This is the entire derivative. I have no idea what a graph of this thing looks like. It's probably some kind of weird, bizarre mess. I don't really care what it looks like, but if I did care what this looks like, and I knew a pair of points, a pair of xy points that were on this graph, I could plug them in here to get the slope of a tangent line. That's one of the things we're going to do with implicit differentiation. We're going to find the slopes of lines tangent to these things. But we're going to find more than slopes. We're going to find the equations of lines that are tangent to these implicit functions. Should be a good time. Let's do another example. Let's do something like x to the 5th minus 2xy plus y squared equals, let me see, if I want to plug in the point 1, comma 2, that would be 1 minus 4 negative 3 plus 4, okay. This all equals 1. We'll say that. So this is an implicit function, x to the 5th minus 2xy plus y squared equals 1. We have an implicit function here. I want the equation the equation of the tangent line at 1, comma 2. So 1, comma 2 is a point on this graph. We can verify that. If you plug in 1 and 2, 1 to the 5th is 1. 2 times 1 times 2 is 4. So 1 minus 4 is negative 3. 2 squared is 4. So it's 1 minus 4 plus 4 equals 1. So this point, 1, comma 2, is a point on this graph. I want the equation of the line tangent to this function at this point. If you're doing a tangent line, this is a brief bit of review from algebra. If you want a tangent line, you need a point and a slope. We have the point, all we need is the slope. We can get the slope using implicit differentiation. So we're going to take the derivative of this whole thing, piece by piece. The derivative of x to the 5th is 5x to the 4th dx. The derivative of this is an exciting adventure. X times y is a product. And to get the derivative of x times y, we need to use the product rule. This negative 2, I'm going to leave that out front for now because it's just a coefficient and coefficients are safe. I'm just going to deal with this x and this y. Product rule says this derivative should be first times the derivative of the second plus the second times the derivative of the first. So that's the derivative of this entire thing. Derivative of y squared should give me 2y dy. And this whole thing equals derivative of 1 is 0. So we got a lot going on, but we can still do our quick little check. Every single one of these pieces should have exactly 1d in it. Is that true? This has 1d. This has 1d. This has 1d. This has 1d. That doesn't count. It's just 0. So we're all set. Every single one of these pieces has a d in it. We're good to go. If we want dy over dx, we need to, I guess the first thing we can do is distribute this 2. 5x to the 4th dx minus 2x dy minus 2y dx plus 2y dy equals 0. If we want dy over dx, we need to get all of the dy pieces on one side of the equation. We need to get all the dx's on the other side of the equation. And then we can factor out the dy's, dx's, and then divide by stuff. So the dy's are already over here. I'm going to move the dx's over. So I'll have negative 2x dy plus 2y dy. These are the dy pieces, they get to stay. No changes. This I'm subtracting out to the other side, so it'll be minus 5x to the 4th dx. This I'm subtracting, I guess I'm adding it to both sides. This will be plus 2y dx. So all my dx's are on the right, all my dy's are on the left. I can factor stuff. This is dy times negative 2x plus 2y. This is dx times minus 5x to the 4th plus 2y. And now I can divide by things. like dx. And this whole bracketed stuff, negative 2x plus 2y. Which should cancel these brackets. So I have dy dx equals, I'm going to say 2y minus 5x to the fourth over 2y minus 2x. Switching the order of each of these pieces a little bit because it is more aesthetically pleasing to me that the positive term comes first, and for no other reason. So I have a derivative. I'm not done yet. The question wanted the equation of a tangent line, for which we need a point and a slope. We have the point. We need the slope.
Sorry, I killed it.
The slope is going to be what happens when I evaluate this derivative at this point. So m equals 2 times 2 minus 5 times 1 to the fourth, plugging in 2 for y and 1 for x, over 2 times 2 minus 2 times 1. I was a little worried for a second there that I'd end up with a slope of, with a denominator of 0 in this slope. I lucked out. So, the slope is 4 minus 5 is negative 1 over 4 minus 2 is positive 2. The slope is negative 1/2. So now I need to create a tangent line. Erase this middle step here. I'm going to use y minus y1 equals m times x minus x1 to create a line. Y stays y, it's a variable. y1 is 2, m is negative 1/2, x is x, x1 is 1. So y minus 2 equals negative 1/2 x plus 1/2. When you add the 2 to both sides, you get y equals negative 1/2 x plus 2.5. That's it. That is the equation of the line tangent to this whole mess at this point 1, 2. So, lots going on there. The quick review is take a derivative implicitly, piece by piece, attaching dy's and dx's to things as needed. You solve the derivative for dy dx by algebraic manipulation. You plug in 1, 2 into your derivative function to get a slope, and then you plug your slope and your point into point-slope form to get a line. That's a lot. This is the kind of question that you're going to see on quizzes and tests for implicit differentiation. It's not as bad as it seems. The product rule gets very fun, as you saw. Chain rule kind of doesn't do much. We can talk about the chain rule real quick. We're already at 14 minutes. Maybe we'll talk about the chain rule in the next video. Stay tuned.